if I told you this structure was never supposed to exist? Not because it's small, but because of where it stands, and yet, here it is. Rising from sheer, unforgiving cliffs. A place where a single mistake could send everything crashing down in seconds. So the question is, how did engineers build something like this? How did they lift thousands of tons of steel to such a dangerous height? Because behind this $170 billion project, it's not just machinery at work. It's a level of precision, so exact, most people have never witnessed anything like it. This is an extremely harsh and unforgiving terrain. Towering mountain ranges, cliffs that are nearly vertical, high altitudes, relentless, powerful winds. For years, this place was considered impossible to access, impossible to build on, and far too dangerous for any large-scale construction. The greatest challenge wasn't weak ground, it was the terrain itself. Engineers were forced to confront sheer rock faces, uneven and unstable surfaces, extreme elevations that amplify wind pressure, and severe difficulties in transportation and installation. There was no stable foundation, no open working space. Everything had to be built, suspended in mid-air. Many experts came to the same conclusion. It is impossible to build here safely. Before construction began, the engineers didn't start building right away. They spent weeks just surveying every inch of the cliffs, using laser terrain scanning, high-precision GPS, and 3D geological modeling. Every single foundation point was identified directly on the rock surface. Small boreholes were drilled to install positioning markers. Each coordinate was recorded, compared against the digital model, then checked again and again. Margins of error were controlled down to the millimeter, because even the slightest deviation in just one support column could throw the entire structure above, completely out of balance. And on a vertical cliff face, there is no second chance to fix a mistake. There was no foundation digging in the traditional sense. No flat ground, no soil to level, no base to prepare. Instead, the entire process began directly on sheer vertical cliffs. Specialized drilling systems were temporarily secured using steel frames anchored into the mountainside. Some equipment had to be suspended by cables, stabilized in midair. From there, the drilling began, straight into the natural rock mass. Each borehole was drilled to depths of 20 meters, 40 meters, sometimes even deeper, cutting through the surface layer, reaching the harder, more stable rock core beneath. But the drilling itself was far from simple. Every hole had to maintain a precise angle, perfect vertical alignment, zero deviation. Even the slightest error would significantly reduce load-bearing capacity. Once drilling was complete, steel anchor rods were inserted, high-strength steel bundles, custom designed for each exact location. They were lowered slowly until they reached the bottom of the borehole. Then, the anchoring system was activated. Concrete was pumped from the bottom upward, not poured from above, but injected in reverse to completely eliminate air pockets, ensuring the concrete filled every void, creating a solid bond between steel and rock. This process had to be continuous, without interruption, because any gap could become a critical weakness. Once the concrete cured, the anchors became part of the cliff itself, no longer separate components, but a unified structure. From that point, the main support columns were fixed onto these anchor points, forming a unique foundation system, not beneath the ground, but gripping directly into the mountainside, a load-bearing system that relies entirely on natural rock and the absolute precision of every drilled hole. The steel components were not made at random. They were manufactured in specialized factories, as separate, precisely engineered modules. Every beam, every pipe segment was pre-cut, drilled, and fabricated in advance, with accuracy down to the millimeter. Then, each piece was labeled and coded, so that, upon arrival at the site, it could be assembled in its exact intended position. But transportation was the real challenge. High mountain terrain Narrow roads, sharp turns. Conventional trucks couldn't reach the site. The components had to be transported using heavy-duty, oversized vehicles, divided into smaller sections, or moved through multiple transfer points. In some areas, components were lifted from the valley below, moved through open air, up to the installation point. Initial assembly. At lower elevations, the parts were partially assembled. Workers began joining individual sections, welding connections, tightening high-strength bolts. Every joint was inspected multiple times, not just visually, but with specialized measuring equipment, because even the smallest deviation would become a major misalignment at height. Once completed, the modules were prepared for lifting. Lifting onto the cliff. High-capacity cranes were installed along the mountainside. Some were anchored directly into rock-fixed points. Each structural segment was attached to a cable system and slowly lifted, carefully, steadily, without vibration. As they left the ground, they moved horizontally through open air, suspended between the cliff and the valley below. Workers at the installation points used guide ropes to control the movement. A deviation of just a few centimeters could cause the structure to strike the cliff, lose stability, and succoot into the void below. Assembly at height. Once the components reached position, high-altitude assembly began. At heights of dozens, even hundreds of meters, workers operated on narrow steel beams. They secured their safety harnesses, maintained balance, moved slowly and with precision. Connections were completed on-site. Welding, tightening high-strength bolts, fixing the structural frame. Strong winds constantly impacted the structure, causing continuous vibration. Every action had to be calculated in advance. There was no margin for error. Reinforcement and concrete placement at height. After the main steel frame was completed, the reinforcement phase began. Concrete was not poured from below in the traditional way. Instead, high-pressure pumping systems delivered concrete to extreme heights. Through long pipeline networks, workers stood on suspended platforms, controlling the flow, distributing the concrete evenly across the structure. The process was carried out layer by layer, pouring, leveling, allowing it to stabilize, then continuing with the next layer. At the same time, additional reinforcement systems were applied. Vibration control, increased structural stiffness, overall system stabilization, piece by piece. Everything fused into a single, unified mass. Technical control. Throughout the entire construction process, sensors were installed across the structure. They continuously monitored structural displacement, wind-induced vibrations, load distribution. Data was transmitted in real time, back to the control center. Engineers tracked every parameter. If any anomaly was detected, work stopped immediately. A deviation of just a few centimeters could cause accumulated stress and deform the entire system. That's why no step could be skipped. No error was acceptable. Everything had to be precise, down to the millimeter. During the assembly process. When most of the structure had already been lifted onto the cliff, a small deviation began to appear. Invisible to the naked eye, no obvious warning signs, but the sensor system detected it. One section of the structure had shifted off its original design axis, just a few centimeters, but on a vertical cliff. That margin was no longer small. It altered the load distribution, created unwanted torsional forces. Pressure began to concentrate on one side. If construction had continued, the entire system could have lost balance, triggering a cascading collapse. Immediately, a stop order was issued. All high-altitude operations were halted. The entire site fell into a holding state. The engineers returned to the data. They didn't rely on instinct. They relied on calculation. The entire system was re-simulated. Every parameter was analyzed. Rock anchor points. Tension forces within the steel members. Connection angles between modules. Adjustments were made step by step. Some anchor points were further reinforced. Certain joints were loosened and retightened. Structural angles were corrected precisely according to the model. This process was not fast. It took weeks, slow, deliberate, continuously verified, until every parameter returned within safe limits. The structure gradually stabilized, and the project could move forward again. Asterisk, asterisk. The final segment was lifted into place. Asterisk, asterisk. A massive pipe section, weighing dozens of tons, hooked into a cable system and slowly raised. Steady, controlled, without a single vibration, it moved across the cliff, suspended in open air. Workers at both ends held guide ropes, adjusting every small movement. The gap narrowed. Clearances checked continuously, just a few millimeters, yet determining the entire outcome. When it reached its final position, alignment began. No room for trial and error, no second attempt. Every connection point was guided into place, perfectly matching the system assembled before it. Then, locks were tightened, welds secured, additional reinforcement applied, and at that moment, the entire structure was sealed. No gaps, no further adjustments, a completely closed system. Asterisk, asterisk. Inside the structure, asterisk, asterisk. A continuous technical corridor stretched along its length. Metal surfaces finished with uniform precision. Lighting ran along the inner walls. Continuous, stable, without a single dark spot. Operational systems were integrated throughout. Asterisk monitoring sensors, asterisk control systems, asterisk technical routing lines. Every internal parameter was controlled. Asterisk temperature, asterisk pressure, asterisk vibration. No wind, no external interference. Only a space, engineered for absolute precision. Asterisk, asterisk. After completion, asterisk, asterisk. The entire system was tested again. Every joint, every structural element, every technical parameter. A series of tests were conducted. Asterisk load testing, asterisk stability verification, asterisk operational trial runs. Data was continuously monitored, compared against the original design. When everything met the required standards, the project was officially completed. The engineers stood still, looking up at the structure suspended against the cliff. It was more than just a construction. It was the result of thousands of calculations. The project was handed over, ready for real-world operation. They said, it couldn't be built on a cliff. That height couldn't be controlled. That safety couldn't be guaranteed. And yet it was done, not because of luck, but because they understood precisely what they were doing. Every number, every angle, every force, all calculated. And in the end, limits didn't disappear. They were simply overcome by those willing to build where no one else dared to begin.